Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. So today we are going to discuss another topic from the course Electrical Circuits, which is network theorems which related to the AC circuits, because we have already previously discussed the network theorems, various networks theorems like superposition theorem, Thevenin's reciprocity, maximum power transfer theorem. And in this class, we are going to discuss especially the superposition theorem and as well as the Thevenin's theorem related to the circuits with AC. So first, let us discuss about the superposition theorem. So before going to solve the problems with the AC network, so let us again remind what is superposition theorem in briefly. So as we know, the superposition theorem, not only the superposition theorem, all network theorems can be applicable for only the linear, active and bilateral networks. Okay. So, and also which I mean, especially for the superposition theorem, it can be, applicable, or it can apply for the networks which are linear, active and bilateral, those having more than two sources. Okay. And the sum of the responses obtained from each source considered separately and all other sources replaced by their internal resistances. So which means, suppose if there is a voltage source, then the voltage source is replaced with the short circuit, and if there is a current source, then the current source is replaced with the open circuit. So which means here, suppose let us consider an electrical circuit. Here, if you want to find the current flowing through the resistor R3, of course here you can see this particular network having two sources. One is voltage source, namely Vs, and another one is the current source, which is Is. So first we should find the current flowing through the R3 by considering each source independently and neglect the other source. And by neglecting the other source, just if it is a current source, then the current source must be replaced with the open circuit, and if it is a voltage source, then the voltage source must be replaced with the short circuit. Which means, suppose in the first case we are considering only the voltage source alone, Vs, then find the current flowing through R3, which is, let us consider I1, and the current source Is is replaced with the open circuit. Then find I1, and in the second case consider the current source Is is alone and replace these Vs with the short circuit. Okay, and then find the current flowing through R3 again, which is, let us consider I2. Then the total current which is flowing through the R3 in the main circuit is I, which is equal to I1 plus I2. This is about the superposition theorem. And we have considered some example to solve the superposition theorem, or to find the current by applying the superposition theorem for the DC excited networks. So now we are going to solve the problems with AC networks. So let us consider here, this is the circuit. So for the circuit, find the current flowing through this, the reactance XL2, okay, which is 4 ohms, by using the superposition theorem. So first here, as we can see, there are two voltage sources are there, AC voltage sources. One is E1 is equal to 10 volts at an angle of 0, and E2 is equal to 5 volts at an angle of 0. So here they have given the values in terms of polar form. And another thing, there are three reactants are there. Okay, I mean, one is the inductive reactance XL1, which is equal to 4 ohms, and then another inductive reactance XL2 is equal to 4 ohms, and another one, the capacitive reactance XC, is equal to 3 ohms, right? So now, instead of representing XL1, XL2, XC, so here let us just redraw this circuit by replacing all these inductive, the reactances with the impedance simply Z1, Z2, Z3. So here let us redraw this circuit and by replacing these impedances with the by replacing these reactances with the impedance. So here XL1 is replaced with Z1, and XL2 is replaced with Z2, and XL3 is replaced with Z3. So now we are going to apply the superposition theorem for this particular circuit, right? So here the same way that we have discussed previously. So we should consider each source independently. At a time one source, okay, independently, and all other sources are replaced with the open or the short circuit. If it is a voltage source, then short circuit, and if it is a current source, open circuit. So now, and let us write here the Z1 is equal to what is that Z into XL1, and which means Z into XL1. So here XL1 is equal to 4 ohms, so which is J into 4 ohms. And similarly Z2 is XL2, so here XL2 value is 4 ohms, so J into 4 ohms. And here XC is 3 ohms, so minus JXC is equal to minus J 3 ohms. Okay, actually here Z is equal to, as we know, what is R plus JXL. Okay, but here R is equal to 0 in all the cases, so that's why instead of representing R here, simply the J into 4 ohms, which means here 0 plus J into 4 ohms. This is actually form, but here R is equal to 0, so that's why we are directly taking the values of the given reactance values, right? So now first let us consider E1 voltage source alone. Then here E2, the voltage source E2 is replaced with the short circuit. And now in this case, now we have to find the current flowing through the Z2, which is I dash. Then how to find I dash? So before going to find I dash, okay. So of course here the one way to find the current flowing through I dash is just simply applying the loop analysis. But instead of applying the loop analysis here, by using the current division rule, we can find the current flowing through the Z2. So for that we need to find the total current which is flowing through the source, which is E1, the source. So let us consider here the total current flowing through the E1 or Z1, which is, let us consider IS1. So first let us find IS1. So if you want to find IS1, first here, as we know, the Z1 and Z2 are in the what is the parallel. Okay, so now let us find the equivalent impedance across these two terminals, the equivalent impedance across these two terminals. Okay, so which means now here Z2 and Z3 are in what is that parallel, so that the impedance, I mean the equivalent impedance is equal to Z1 Z2 by Z1 plus Z2. So here which means here Z2 and Z3, so Z2 into Z3 by Z2 plus Z3. So we know the values of Z2 and Z3. Just substitute here and simplify, then you will get the equivalent impedance between the Z2 and Z3, because these two are in parallel. So which is minus J into 12 ohms. So if you convert this one into the polar form, then 12 ohms at an angle of minus 90 degrees. Then of course now here Z1 and Z23 are in series. Then the total impedance, let us consider here Z. Okay, and this Z is equal to the total impedance, here it is Z, which is equal to Z1 plus the parallel combination of Z2 and 3. Then now from the circuit we can able to find the total current flowing through the circuit, which is IS1. So here the IS1 is equal to the what is that, the voltage E1, okay, the voltage E1 by the total impedance in the circuit, which is Z1 and Z, the combination of Z, I mean the Z23. So here Z1 and Z23 are in series. Then here IS1 is equal to E1 by this combination of Z2 and Z3, which is Z23 plus Z1. Then substitute the values of E1, Z23 and Z1 in this equation. So E1 we know that already given in the problem, which is 10 volts at an angle of 0, and Z23 just now we have calculated, which is minus J 12 ohms, plus here what is the Z1 is also given in the problem, it is J 4 ohms. Then if you simplify this, then you will get, okay, what is that value? That value is 1.25 amperes at an angle of 90 degrees. So now we have found IS1. Okay, then apply simply the what is that current division rule. So according to the current division rule, I1, which is equal to the opposite impedance, okay, I mean the total current IS1 into the opposite impedance, which is Z3 by Z2 plus Z3, right? So here this is the current division rule formula, which is I dash, which is equal to the opposite impedance, which is Z3 by Z2 plus Z3 into the total current here flowing through the circuit is just now we have calculated, which is IS1. Then substitute all these values. Now we know Z3 value, Z2 value, and again IS1 value. Then substitute here all these values. Then you will get the I dash is equal to 3.75 amperes at an angle of minus 90 degrees. So this is with respect to the what is that by considering one voltage source, which is E1. So which means here the E1 is the active voltage source and E2 is replaced with the short circuit. Now we are going for the second case, so which is this is I dash. Now for the second circuit here, in this case, now we are going to consider the second voltage source E2 alone and the first voltage source E1 is replaced with the short circuit, because here in this particular circuit, two are the voltage sources only. There is no current source. Then now here also again we need to find the current flowing through the Z2. So let us consider in this case the current flowing through the Z2 is I double dash. Then here the same procedure that we can follow, which we have followed in the first case. So here also we can find the total current. Let us consider in this case IS2. Then after finding the total current IS2, then again apply the current division rule to find the current flowing through the Z2, which is I double dash. So for that again first we need to find the total impedance. So for that here Z1 and Z2 again are in the parallel. So here then the Z12 which is equal to the Z12 which is equal to Z1 Z2 by Z1 plus Z2. So here because here instead of that we can simply write Z12 is equal to Z1 by N, because here Y instead of Z1 actually the equation is Z1 Z2 by Z1 plus Z2, right? But here instead of this Y Z1 by N means, because here the value of Z1 and value of Z2 are same, which is 4 ohms. Okay, so which is just now here we have seen which is J4 ohms. So that's why here instead of writing this here Z4 ohms by 2, then you will get here it is J into 2 ohms, that is Z12. Then again find the value of the IS2. IS2 is equal to the total voltage, here it is E2 by Z12 plus Z3. Then substitute the values of E2, Z12 and Z3 here. Then after simplifying these, then you will get the IS2, the total current in the second case is 5 amperes at an angle of 90 degrees. Now, of course, again in the current division rule also we can simply, because here the total current is 5 amperes and the 5 amperes is divided into the same proportion, because here Z1 is equal to Z2. So that's why instead of writing here what is mean that I double dash is equal to the total current IS2 into here the opposite impedance is Z1 by Z1 plus Z2. Okay, or simply you can write I double dash which is equal to IS2 by 2, because here again the impedances are same. So that's why here I double dash is equal to IS2 by 2, which is 2.5 amperes at an angle of 90 degrees. So now we have calculated I1 and I2. Then to find the total current I, for this we need to add I1 and I2. Okay, but here instead of adding I1 and I2, so here as you can see here the direction of the I1 and I2. So here I1 is in this direction, which means let us consider here it is A. So A to B, but I dash is here B to A. So that's why, so suppose if you want to take the reference current direction is same as the I dash direction. So that's why here I dash having the positive sign, but the I double dash direction is opposite to your reference current direction. So that's why here we have to place minus I2. So which means exactly the equation is I is equal to I dash plus, okay, so minus I double dash. So that's why if you simplify this, then I dash minus I double dash. Right, then substitute here the values of I dash and I double dash in this equation. Then you will get finally the total current flowing through this particular circuit I, which is equal to, or the current flowing through the reactance XL2, which is 4 ohms, is equal to 6.25 at an angle of minus 90 degrees. So this is the way we can find the current flowing through any resistor by using the superposition, any reactance or any impedance by using the superposition theorem when the input is a DC excitation, AC excitation, right? So this is how we can solve the problems, right? So now let me consider, here you can see here this I1 is in this direction and I2 is exactly opposite to that particular I1 direction. So both are opposite to each other. So that's why here I is equal to I1 minus I double dash. Suppose if if we take I as in this direction, okay, then now I is equal to, in this case I is equal to what is that, minus I1 I dash plus I double dash. It is depends on the reference direction which we are considering. Okay, Now, yeah, let us discuss another problem with the superposition theorem. But here, in the previous case, I mean, unlike in the previous case, one voltage source and one current source is there, because before it was two voltage sources are there, but now in this case, one current source and one voltage source is there. So here now, by using the superposition theorem, we have to find the current flowing through the 6 ohms resistor. Okay, the current flowing through here R, this is the 6 ohms resistor. Okay, so this circuit having one impedance, one reactance, okay, I mean inductive reactance XL, which is equal to 6 ohms, and another one is one capacitive reactance XC is equal to 8 ohms, and another one is the resistor R is equal to 6 ohms. And there are two sources. One is voltage source. The voltage source E1 is equal to 20 volts at an angle of 30 degrees, and the current source I1 is equal to 2 amperes at an angle of 0 degrees, right? So here again, the same way, first we will consider, first let us replace all the, the reactances with the impedances, because here, this we can write X R plus or R minus J XC, okay. So that's why here, this total can be replaced with the impedance Z2, and this one can be replaced with Z1, right? So now, at a time we should consider only one source active and another sources should be replaced with open or short circuit. So the same way, so first let us consider the current source alone, then the other voltage source is replaced with the short circuit, then find the current flowing through the Z2. Let us consider here it is I dash. Then again, a similar way for the second circuit, okay. In the second case, we should consider the current, the voltage source alone, and the current source should be replaced with the open circuit, because we know already the condition, all the voltage sources are replaced with the short circuit and the current sources are replaced with the open circuit. So by replacing the current source with open circuit and find again the current flowing through Z2, so let us consider here it is I double dash, then the total current flowing through this particular circuit I is equal to here I dash plus I double dash, because here I dash and I double dash both are in the same direction as the I direction. So that's why here there is no change in the sign, because there is no change in the direction. But in the previous case, I dash and I double dash are directions are opposite to each other. So that's why there the I is equal to I dash minus I double dash, right? Because I double dash direction is opposite to the I direction. So that's why we made the equation like that. But here the all current directions I1 dash and I2 dash, or I dash and I double dash all are in the same direction. So that's why here I is equal to I dash plus I double dash, right? So first let us consider the first circuit, okay. We are considering the current source alone and the voltage source E1 is replaced with the short circuit, okay. So here Z1 is equal to J into 6 ohms and Z2 is equal to 6 ohms minus J 8 ohms. So here we need to find the current I1. Okay, so then how to find, not I dash, not I1, I dash. Then how to find the current I dash here? Okay, so here to find the current I dash, here we can apply again the same current division rule. Okay, so here because this is the current, total current is I1 and the I1 is divided, some of the current is flowing through the Z1 and some of the current is flowing through the Z2, right? So here by apply, if you want to apply the current division rule, then here I dash is equal to, what is the total current here? The total current is I1. So I1 into, and where we need to find I dash means in the Z2. So the opposite resistor, opposite impedance is Z1. So Z1 by Z1 plus Z2. Right. So here, if you substitute the values of Z1 and Z2 here, Z1 is J into 6 ohms. J into 6 ohms by again J into 6 ohms plus here Z2 is 6 ohms minus J into 8 ohms, right? Into here I1 is again, what is the value of I1 that they have given in the problem? Let me see here, I1 is equal to 2 amperes. Yeah, I1 is equal to 2 amperes. Then if you simplify this, you will get the value of J, because 6 into 2, 12. So J 12, because this is the current amperes by, so here 6 is same as it is, okay, 6 minus J 2 ohms. So if you simplify this, then you will get here 1.9 amperes at an angle of minus 18.43 degrees. So which is I dash, right? So here I dash is equal to 1.9 at an angle of minus 18.43. So the similar way, if you go for the second circuit, okay, in the second circuit, we are considering E1 alone, okay, and the current source is replaced with the open circuit. Then find the current flowing through I double dash. I mean current flowing through Z2. This is I double dash. Okay. So this is very simple because here this is old circuit because and Z1 and Z2 are in series. So then here the total, I mean the current I double dash, which is equal to the voltage E1 by Z1 plus Z2 because both are in series. Then here the voltage E1, which is equal to 20 volts at an angle of minus 30 degrees. No, sorry, not minus, plus 30 degrees. By here the value of Z1 is what is the value of Z1? Just now we have find that is J 6 ohms plus the value of Z2 is 6 ohms minus J 8 ohms, right? So if you simplify this, then you will get the final value of I double dash. I mean, if you are converting into again into the what is that, the polar form. So here I double dash is equal to 3.16 amperes at an angle of 48.43 degrees. Okay, so this is I double dash. Now the current flowing through this 6 ohms resistor I is equal to I dash plus I double dash. So here I dash that we have calculated is 1.9 amperes at an angle of 108.43 plus, and I double dash here it is 3.16 amperes at an angle of 48.43 degrees. Then if you what is that, add these two values, then you will get finally, which is 4.42 amperes at an angle of 70.2 degrees. So now this is the total current I which is flowing through the 6 ohms resistor. So this is how we can find the current flowing through a particular resistance by using the superposition theorem. Okay, because in the previous case we have only discussed with the DC excitation. Now here which is the AC excitation, right? And next we are going to discuss about the Thevenin's theorem. So in the Thevenin's theorem, as we know, by using the Thevenin's theorem, how to find the current flowing through the load resistor. So first in the Thevenin's theorem, it is very important to know that how, I mean, we should convert the whole circuit into the Thevenin's equivalent circuit. So here the Thevenin's equivalent circuit having the Thevenin's voltage and the Thevenin's resistance in series with the load resistance RL. So here R is the load resistance, then this can be converted into if the Thevenin's circuit of this particular is, okay, the Thevenin's voltage source. Okay, let us consider here it is E Thevenin's, and in series with, okay, so let us consider here it is Z Thevenin's and the load resistance R. Then here the current I is equal to E Thevenin's by the Z Thevenin's plus RL. Let us consider RL. This is the way to find the, applying the Thevenin's theorem to find the current flowing through that particular load resistance, right? So then the same theorem we are applying for the AC networks. So for these AC networks, okay, again here also we are just instead of representing the capacitive reactance and the inductive reactance, so instead of that here we are replacing this with the Z1 and Z2. So anyway, first there are two conditions. Okay, first we need to find the Thevenin's voltage, and then after that the Thevenin's resistance. To find the Thevenin's voltage, what we have to do is, first where we have to find the Thevenin's what is that voltage. Okay, so I mean across the load terminals, I mean just replace the load terminals with the open circuit and find the open circuit voltage across those two terminals. That is called the Thevenin's what is that voltage. Okay, so for this here I have just replaced with the R, the load resistance, with the what is that open circuit. Then find here the Thevenin's voltage across these two circuits. So to find the Thevenin's voltage across these two circuits here, so E Thevenin's, that is again here as you can see, these three, what is that, the voltage source E and the impedance Z1 and impedance Z2 are in series. So simply we can apply the voltage division rule to find the voltage across the Z2, because here the voltage across these two terminals is nothing but the voltage across the Z2. Okay, so here the voltage across the Z2, how we can find is, so which means here the voltage across Z2 are, which is E Thevenin's. So E Thevenin's is equal to Z2 in Z2 by the total impedance Z1 plus Z2 into the total resistance, which is the total voltage E. So then substitute here the values. Here the Z2 value is minus JXC. Here Z2 value is minus J2 ohms by, here Z1 is J8 ohms minus J2 ohms into, here E is equal to 10 volts at an angle of 0 degrees. Then if you simplify this, then you will get the E Thevenin's, which is equal 3.33 volts at an angle of minus 180 degrees. So this is E Thevenin's. Then now next we need to find R Thevenin's. So for the R Thevenin's, I mean first where we need to find the R Thevenin's, again across the load terminals. And to find the R Thevenin's, the condition is we should replace all the active sources, okay, all the active elements with open and short circuit, which means if it is a voltage source, then that should be replaced with the short circuit, and if it is a current source, then that should be replaced with the open circuit. Anyway, here we are having only one voltage source, and then voltage source is replaced with the short circuit, right? So here how Z1, I mean now we have to find the equivalent resistance between these two terminals. So here Z1, Z2 are in the parallel. Then here the Z Thevenin's, which is equal to Z1, Z2 by Z1 plus Z2. Then substitute these values here, J8 ohms into minus J2 ohms by J8 ohms plus, of course here minus J2 ohms. Then if you simplify this, then you will get here 16 ohms by 6 at an angle of 90 degrees. And if you further simplify this, this is 2.67 ohms at an angle of minus 90 degrees. Now we have calculated the R Thevenin's value, R E Thevenin's value, and as well as the Z Thevenin's value. Then substitute these values in the Thevenin's equivalent circuit. So here E Thevenin's is equal to 3.33 volts at an angle of minus 180 degrees, and here the Z Thevenin's is equal to 2.67 at an angle of minus 90 degrees, right? Okay, or in another words, okay, because here this is the Z Thevenin's, okay, this is minus 90, so we can replace this with the capacitive reactance. So exactly then E Thevenin's is equal to 3.33 volts at an angle of minus 180 degrees. And here XC, that is the capacitive reactance, is equal to 2.67 ohms into 2.67 ohms. So this is the way to apply the Thevenin's theorem for the AC circuits also. In the next class, we will discuss what is the remaining theorems for the AC networks. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.